I want to start off by saying if you have any questions during the talk, please feel free to, I don't know what the protocol is, either put it in the chat or call it out. I'm happy to field questions at any point during the talk. And please do speak up. There will be one point where I'll be asking a question and I'll be happy to have some people's ideas thrown out. So please don't be shy. Okay, so this work, this anomaly detection work was done a couple years ago at a workshop at the Institute for Computational and Experimental Research in Mathematics, which is a really cool math institute. And I would recommend keeping an eye on it as you continue throughout your mathematical career. I don't know how many programs they have for undergraduates, but certainly graduate students, postdocs, and researchers. It's a really cool place. And so this was work that was done there. I have also listed my collaborators that help, that we all work to do this project. So, all right, without further ado, let's go ahead and sort of look at an overview of what we'll talk about today. So first, I want to start off with sort of a warm-up problem, kind of a toy problem, that will kind of give us a flavor of some of the important pieces that we'll need to understand the sort of more real-life problem that comes after. I'll talk about some tools, some more concrete tools. I'll talk about the single measurement vector problem, multiple measurement vector problem, and then finally this problem of anomaly detection that we want to address. And then I'll talk about some of the actual results that we had. Okay, so let's start off with the toy problem. Okay, here is the toy problem. And some of you may have seen this or variants before, but it's deceptively simple. It actually takes a little sit down and a little bit of a writing out to kind of come up with a solution. You think you have it and then you don't. So let's go ahead. I'll just go ahead and read this out. So we have 12 balls and they're all the same size. Now 11 of the balls are the same weight, but one is a different weight. You don't know whether this ball is heavier or lighter than the other balls. And then we also have a balance. So I've put this little nice cartoon picture here, one of these guys, a balance on which any of the balls can be weighed against any other group of balls. Okay, so the objective is within 3 weighings, determine which ball is the anomalous ball, the one that's a different weight, and determine whether it is heavier or lighter than the other balls. So there's kind of 2 pieces that we want, 2 pieces of information that we want out of this. Okay, so maybe first forgetting the 3 weighings. So let's just pretend you have an infinite number of weighings. Does anyone want to sort of throw out there just whatever idea of like how you might get started, finding which ball is a different size, even just like a basic approach? Does anyone have anything they want to throw out?
Divide the balls into like 2 groups and then weigh each group and then divide the heavier or the lighter one, I guess.
Yeah, that's awesome. That's great. Yeah, so possibly even more naively, right? One thing we could do is just like take pairs of balls, right? And just start weighing them against each other. And then like, maybe we'll get lucky, right? Maybe we'll get lucky and on our first try, we'll put 2 balls on the scale and they'll be unbalanced, right? And then we'll say, okay, one of these is the anomalous ball, because if it's balanced, then we know we have 2, actually we get information both ways, right? So if we take 2 balls, put them on the scale, and the scale is balanced, right? We know that both of those now represent the prevalent ball, the ones that are like mostly the same size. And then we can now take one of those with confidence and then just weigh against the other balls until we find a discrepancy. And if it's heavier, and we'll know whether it's heavier or lighter too when we meet that other ball. That's going to take a lot of weighings though, right? That's going to take like, best case, the very next one we weigh, it will tell us. And so that will be like 2 weighings. But worst case, right, we're going to be just like weighing all, against all 12 balls, and it's going to be a lot of weighing. Then, as you pointed out, I'm not sure. I don't know names, so as you pointed out, we can group balls together, right? Like maybe we could divide them in two, right? And put half the balls on one side and half the balls on the other. And since one of them is different, one of those sides is going to be opposite the other, right? But it's still not. I mean, we definitely have more work to do, right? Because we're not close to. If we get lucky, maybe we'll do it in 3 weighings, but we're not close to guaranteeing that we're going to get there in 3 weighings. Okay. And yeah, I'm seeing more suggestions on the chat, and I can see the beginnings of like a really good approach to this problem. And I encourage you to keep thinking about it because it's just a fun problem, and eventually you'll kind of get to a solution. But do check it with other people, because when I first wrote out a solution, I was like, oh, this isn't so bad. And a colleague of mine was like, yeah, no, that's not right yet. We don't know in this case or whatever. So make sure that you chat with others about it too, because it's easy to miss something. Okay, so let's. There we go. I'm going to introduce one approach. So this is different. My initial approach was kind of like the types of things we've started describing. You know, it was sort of this adaptive approach, right? You make some decision about what groups or which balls you want to weigh or leave off. And then you, based on the information that you get from that weighing, you'll have a strategy to pick your next weighing, right? And so this is an approach that I was really excited to find. This isn't mine, but it's one that I found on the internet, where it gives you a way of having a deterministic solution. So that is to say, you can apply this, and no matter what, you know, what happens or how you, you know, do it, it gives you a prescribed way to find which ball is anomalous and whether it is heavier or lighter. So here's the setup. Here's what we're going to do. Each of these X's represents one of the balls. Okay, so we've got our 12 X's, and then we've got this matrix. Okay, and each row represents one of the weighings. Okay, and so if we put a 1, that means that ball X1, we're going to put on the left side of the scale, one of the sides, let's say the left side. And a 0 means we're going to leave it off the scale. And a -1 means we're going to put it on the right side of the scale, say. Okay, and so this is telling us what each of our weighings is going to be. And we have 3 weighings. Okay. So then, okay, I've just now sort of put this, reconfigured what we just had on the previous slide, right? So here's that matrix A with the 0s, 1s, and -1s. Here's our ball vector, and I've just sort of zeroed out in this example which one is the one we're going to find. We don't know that yet. Okay, and so what do, right? We can take the measurements. So we take the measurements, right? We do our matrix multiplication, row dot column, and we're going to get a value for the first row, row dot column. We get a value for the second row, and so on. And so now with these values in hand, how do we recover which ball is the anomalous ball, and how do we know whether it's heavier or lighter? So I'm going to go ahead and ask again, can anyone see how we might want to do this recovery? Okay, so someone says for the first case, let's see. For the first case, we know the anomalous ball. It is not included in the weighings, first weighing. Okay, let's see. Yeah, that may be. Let's see. I'll just go ahead and I'll go ahead and tell you you're going to kick yourself, and then maybe that is what you were saying, and if so, I apologize. But okay, so what we're going to do is notice that one of these columns, right, is going to wind up corresponding to our values that we got out from the measurements, right? And this is the location of the index of this column corresponds to the index of the anomalous ball, right? And it corresponds up to sign, right? So if this were 0, -1, 1, that would mean one thing, the ball was heavier. And then if it was if it's this exact match, that means, oh, it's lighter, right? So that captures all the information we need to recover which ball, and in addition, whether it was, you know, sort of like some amplitude information too, whether it was heavier or lighter. So that's how we would do this recovery for this problem. I really like that sort of deterministic solution. That is to say, it doesn't rely on sort of any uncertainty about like the order we do the balls in or whatever. This will always work. And so it illustrates some important concepts in this sort of field of compressed sensing that we need. And so one of those things is this trade-off between the rarity of like the ball, most of the balls were the same, right, and only one was different, or sparsity. That means like having lots of zeros in our system, our matrix, or our signal, and the necessary number of weighings or measurements, right? So we could, because that different ball was so rare, we could identify it with many fewer measurements than we would need if there were many, you know, if there was lots more going on. There's just not a lot going on. We can treat all those other prevalent balls as sort of background. Okay. It also kind of demonstrates sort of this idea of designing a measurement matrix, right? And designing how we're going to measure. So there's these techniques for measuring signals in compressed sensing that are adaptive, right? You take a measurement, and based on the value you get out, you make your decision about how you're going to take your next measurement. Or you might have something deterministic. That is, you're going to apply these measurements no matter what, and you're going to do your recovery, your signal recovery from there. And then also you can just take random measurements, right? So that turns out to be extremely effective in situations where you have sparsity or rarity in the information that you're trying to measure and recover. And then, of course, the recovery strategy. Like, are we just interested in which ball it is, or are we also interested in some amplitude information? Like, are we just interested in like where the anomalous locations are, or are we also interested in like actually recovering the full signal, right? Or understanding whether it's heavier or lighter in the case of the toy. Okay. So next we're going to go to tools, and we're going to make these things a little bit more mathy now. Okay, so this is called a single measurement vector problem. So it looks very familiar, right? X is what I'm calling our sort of signal, right? You might think of these as like 12 sensors that are going to have values at any given time, and we're trying to measure the output given, and what we're going to record is what's here in Y. And here A I've just depicted as kind of a random matrix, right? So this is the single measurement vector problem. And how do we solve this problem? Okay, so this is classic, right? Classic optimization. We have AX equal to Y, and X is unknown, and we want to subject that to a constraint. So here, this notation is sometimes called the L0 norm. It's not really a norm, but it is just symbolizing the number of non-zero entries. Okay, so we want to minimize the number of non-zero entries. We want to find the sparsest solution to this system of linear equations, right? Okay, so yeah, this L0 thing is not complex. And so this sort of represents a combinatorial optimization problem. It's a very hard problem. And so what often is done, right, is you'll take what's something called a convex relaxation. Okay, and so this is now, instead of that 0 norm, we have this 1 norm, right? And the 1 norm, you've probably learned, is just the sum of the absolute values of the elements of your vector, right? And so this optimization problem is sometimes called basis pursuit. And here you can apply linear programming techniques. And so, but we can't just like change to the one norm for every system. And so we have to say, what are some sufficient conditions for identifying the same solution as the L0 minimization problem? Okay, and so one of those conditions, it's going to depend on the sparsity of X, how sparse X is, and the sort of orthonormalness of the columns of our measurement matrix. So what do I mean by that? Well, there's this whole property that's studied a lot in compressed sensing called the restricted isometry property. Okay, so isometry is one of those words that gets thrown out there, and I sometimes forget what it means and it sounds so fancy, but right, it's just iso, so same, metry, distances, so same distances. So it's an isometry is a preserves distances, right? We learned from linear algebra, one of the big takeaways of linear algebra, right, is that a matrix is just a linear transformation that takes one vector and transforms it into a different vector, right? And so a matrix having the restricted isometry property means that when it does its transformation, it's going to sort of approximately preserve distances, and so we don't really need to know like all the technical details of that, but we just know that some examples of this are if we take a Gaussian random matrix or a Bernoulli random matrix, those random matrices will have this property, which is really cool. And so we can, if we have a sparse X, we can apply, even a random matrix and have a pretty good hope of recovering the correct solution. So now I'm going to pop up something that probably looks familiar, especially to any data scientists in the audience, right? So this is lasso. This is a form of that basis pursuit, or that L1 optimization problem that I showed on the previous slide. And so, yes, sklearn, right? This is probably familiar. I put that up there because I use sklearn to do what I'm going to describe next. So we're just going to do a little experiment. And we're going to see how good these random matrices are at recovering your sparse solution. Okay, so here we have our measurement matrix A. This is a Gaussian random matrix. We have our signal here, our X, and it's very sparse. All these gray squares are 0, and we have one place we're trying to recover. And so here is the measurement values. And so we're just going to run a bunch of trials, and we're going to try to recover the signal with one measurement. So just using one of these rows, with 2 measurements using 2 of these rows, 3 measurements, and so on. And we just want to recover the support, right, location. So what I mean by that is just the index, just the place. We don't like it's an arg that we want, with an argmin that we want out or whatever. We don't want the we don't care about the amplitudes in this case. So we just want to recover that location. So that's the support. And so what this plot tells us, so we can use lasso to do that if we want. And lasso is going to return some sort of coefficients, right? Some regression coefficients, and we're going to order those, and we're going to take the wow, I suddenly don't know if it's the smallest or biggest one, whatever. We're going to take one of the extreme ones, and we're going to then see if that is the location of the non-zero entry, and then it's going to be a success if it is. Okay, so we're gonna do a bunch of these trials, and we're going to see the proportion of successes to failures, and we can see by the time we hit 3 measurements in this setup with these 12, this dimension 12 vector, we're getting pretty accurate recovery of the support location of the signal, which is pretty cool, because before we had these like carefully constructed, deterministic measurements, but we can pretty much do it randomly too with just 3 measurements. Anyway, I think that's pretty cool, and it's important to keep this setup in mind, because when we do the real experiments, we're going to have things like this too. So remember, this is sort of just depicting when we have a success, like the proportion of successes to failures, so sort of how accurate our recovery is as we go up in the number of measurements. Okay. Is that okay? Are there any questions? Okay, let's go on to distributed compressed sensing. Okay, so we talked about when we just have one signal. Let's see, we have one question here. Let me go ahead and look at it. What about in the non-sparse case? Yeah, so in the non-sparse case, sort of more bets are off, right? We know that when you have a linear system, if you have, you know, you need sort of at least as many variables as you have, or at least as many equations as you have variables in order to like solve everything accurately, right? But the sort of sparsity constraint says, okay, you don't need that many if you, you know, if you're trying to encourage sparsity. And you can kind of think about that, like in our ball example, how if we didn't have that, it was the only one that was like that, it would be much harder to sort of extract like which ball we were looking for or whatever. So I think I'll leave it at that. I don't know quite how to make that more clear either. Is that okay? Would you prefer to refine the question? Okay, cool. All right, great. Okay, so multiple measurement vector problem. So now instead of just one set of sensors or you know, one high dimensional signal, right? Maybe we have a whole array of sensors, or maybe we have one set of sensors, but as it goes through time. So each of the columns might be as it goes through time. And we want to sort of measure them all at once and recover them all at once. And if things going on are, so like maybe you think of this as like each column is a self-driving car, and this is their set of sensors, and you're trying to look at them as a fleet and decide what's going on in with their various things. And maybe this is way too many sensors to measure and to store information about individually, but you take these measurements and you store these smaller amount of measurements. And then you want to be able eventually to translate back to recover information about what was going on in the system. And so that's a hard problem, but what happens is you don't often get this like randomness. Oftentimes there's a lot of correlation what's going on, especially if you think of this as one set of sensors over time. You know, maybe not much is changing, right, over time. And it's mostly like the interesting stuff is mostly happening on at a few locations. And now what we can, when we try to measure everything all together, we can take advantage of that to be more efficient, right? So this is kind of going up another step and trying to like juice this sort of setup to get the information we need more efficiently. Okay. So there's a paper that introduced these joint sparsity models. So that is to say, each one of these vectors is sort of individually sparse, but they're also they also sort of share the same support, right? It's the same locations that are the non-zeros across the whole set of signals. So one of the models that they introduced in this paper is one where everything is zero. They call this the joint sparsity model, JSM2. Everything is zero, and you have a few locations, a sparse number of locations that can vary in accordance with some distribution, okay? And then they have another model, a JSM3 model, joint sparsity model 3, where you don't have zeros, but you have a common background component, and then you have some sparse innovations. So there's certain locations where you're allowed to have sort of a non-common distribution going on. And so what does that look like? We can break it down. So here's the common component, This is the background. So it's not zero, but it's all consistent across the columns. And then these are the sparse innovations. So they are sparse, so there's zero in the background here. And then you're allowed at certain sparse locations, a certain sparse support to vary in distribution. Okay, and so if you sum them up, this is what you get. So this is this other signal model that they came up with. Now, what we want to look at, since we're interested in anomaly detection, hang on, okay, there we go. So instead of having a sparse signal, maybe we have a rare probability distribution, right? So maybe we have a collection of random variables where just a few are distributed differently. So these here I have as an example a bunch of a bunch of random variables distributed normally, but here X3 is distributed, has slightly different parameters, right? And maybe we want to detect the location of that different random variable. So how would we do this, right? How do we tell the difference between distributions, right? We usually have to take samples from them, and then we have to conduct hypothesis tests. That's what we do. And but now we want to infer statistical information from the signals following distributions, not just raw signal recovery. So it's not just that we're getting data in over time. Like we actually want to infer information about the distribution. And so an example of this is something called network tomography, where you kind of have where you have a network and it's kind of a black box, and you're trying to like put together how things are interconnected and what's going on inside that black box just by information that you have from sort of the boundary. And so one of the problems in network tomography is detecting these congested links with abnormal delay statistics. So this would sort of be an example of where this setup might come up. Okay, so how would we detect which distribution is different? So right, as I was saying, you could sample individual random variables and conduct hypothesis tests in order to differentiate the distributions. Well, that's going to be an awful lot of samples and an awful lot of hypothesis tests if we want to do it that way. So another idea is to, instead of sampling the distributions individually, maybe we want to sample linear combinations of the random variables, right? So that's doing those linear combinations, right? That's like taking a mixed observation, and we're going to conduct hypothesis tests on those mixed observations. And so now maybe we need fewer samples than if we sampled them individually, but it still requires that we conduct quite a few hypothesis tests that makes this infeasible when you have pretty large dimensions in your system. And so this paper begins to explore some more efficient algorithms, but they don't give recovery guarantees. So we're going to treat this explicitly as an MMV support recovery problem. So MMV was that multiple measurement vector sort of technique that I showed you before. And we're going to see how existing theory and algorithms for the MMV problem can be adapted. And it's going to be more efficient than hypothesis testing. So this is our sort of adapted model. So you remember those joint sparsity models that I showed before. So our JSM2, we've added R to indicate random. This is going to be similar, but it's going to be a little different. So now we have a background distribution that's all common and has mean 0. And then we have locations that follow a different Gaussian distribution. And then for our JSM3R model, we're going to have, it looks similar. We're not sort of requiring that our background be consistent across the columns like that other one was. It's now following one distribution, and then our sparse innovations are following a different distribution. Okay, so here's what they look like in comparison. So this was the sort of signal one, and this is our sort of anomaly detection one, signal one, anomaly detection one. And it's a little different, right? So they look very similar, but the problem is these random variable ones are not truly sparse, right? This isn't exactly 0. And so we have to be sure, we have to be able to guarantee that the algorithms that applied to these two models are actually going to apply to these and accurately be able to recover the signal. So that's kind of our task going forward, is to just make sure that we can still apply the techniques that applied to these other two models. Okay, so here we go. So here's an algorithm, and I always get a little bit overwhelmed when someone throws up an algorithm like this, but we're going to totally break it down in the next few slides. I'm just going to say first, to orient us to this, our input to this algorithm is going to be those Y's, so those measurements that we took. We're going to have a measurement matrix at each time step, and the sparsity, how many sparse locations, there's going to be K sparse locations. And so what we're going to do to recover the support is we're going to compute these test statistics. So this is like our estimate for, well, these are the, this is what's going to give us the support location. So remember, in this case, we're not trying to recover amplitude information. We don't want to recover the signal fully. We're just trying to find if we can detect the support, the locations of the anomalous random variables. Okay, so we want to compute these, and we're gonna perform this. And like I said, I'm going to break it down on the next few slides. And then the sparse support estimate is we're going to pick the K largest of these test statistics, and that's going to tell us where the anomalous support is. Okay, so here we go. Breaking it down. So this is this JSM2R model that I showed before. So we have our background distribution centered at 0, and then we have our different Gaussian over here. And then this is one of these, this is what we want to compute, right, for each n. So n is going this way. This is this 20 dimensional thing here in this little example that I have. And t is going this way. This is 10, this 10 thing. And also we have 10, we have one for each t. We have little measurement matrices. So we're taking 2 measurements at each time step. And then we get these, this is the measurements we get out. Okay, so what are we going to do? The first step, so to compute the first test statistic, the C1, we're going to dot these two things together, take an inner product, square, and then we're going to go down. That corresponds to sort of this first square here. And then we're going to continue. So take the next one. That's this next square, and we're going to go all the way across. We're going to go all the way across until we get to 10 measurements. So that corresponds to sort of this first row. And we're going to sum all those up and divide by t. So we're kind of taking an average across this whole thing. So what this test statistic is kind of doing, this first one we've computed, C1, is sort of an estimate of sort of an average value of this whole first row. Okay, so now we have to do that for all the rows, and then don't you agree that at the end, right, we'll have an estimate of sort of the average value of each row, and then these should be very different than the rest of these. And so by taking, since K is 2 in this case, because we have 2 sparse locations, we'll take the max, the biggest 2, the top 2 of those X's, those test statistics, one for each row, and that should give us the correct support locations. So let's see. So we have to go, we went all the way across. Now we're here at the end. So this is C20, and we're going to do the same thing, go down. Okay, great. Now we have C1 through C20, and we have our estimate for each sort of the average value of each row. And that's going to be, you know, these will probably be larger values than the rest, and those are going to be the ones that are going to surface that the algorithm is going to return as the support locations. And so then we'll have succeeded. So we need to show that this actually works. And so we do this, we have this theorem, right? So this is saying that if you have your AT, so your m by n sensing matrices, and at the with standard Gaussian entries, And then you have your random variables, most of which are distributed with mean 0 and then standard deviation sigma 1. The rest of which are normally distributed with a different mean and a different standard deviation. And then we have some assumptions. So our assumptions on these distributions are that our means the parameters of the distributions are related in this way, and that we're taking at least one measurement per time step. We can't take no measurements per time step. So that's a pretty weak assumption, but it's good. And so then that algorithm that we just looked at, the one-step greedy algorithm, recovers the anomaly index set with probability 1 as t approaches infinity. So that's the theorem, and we're gonna look at a proof sketch of that. Okay, so let's think about this test statistic again. Whenever we see this 1 over t and then summing from 1 to t, this should kind of say to us, okay, average, right? We're averaging something. And so this is actually the sample mean of some random variable. So let's just put this in a black box for now and call this random variable Zn. So we can invoke, since we're dealing with Gaussians, the law of large numbers, and to say that as t goes to infinity, this test statistic is going to be the expected value of this random variable in the limit. Okay, so then we're going to compute the expected value for n in the anomalous indices and without. So for one example for each n, and then we can lean on our assumptions to show that this is strictly larger in the anomalous case than the prevalent case. And so that's how we're able to show that this algorithm will be successful at recovering in the limits. So it's doing something, it's working, and it will be sort of application dependent, you know, how all this kind of shakes out and what choices we want to make. But it does do something. We can use it for this random variable case, even though we technically don't have the same sparsity assumptions that you had in the sort of original setup. Okay. And so here's an experiment on what's called synthetic data. So that just means we generated some random signals and some random measurements, and we're able to kind of evaluate our algorithm this way. So here in this setup, we have n elements instead of 12 or instead of 20. So that we had n equals 100. We're going to have t, so the number of, that's the width of that X matrix. It's going to have 100 columns, or we'll vary t from 0 to 100. We'll vary n, so that's the number of measurements we're taking at each time step from 1 to 100. And then k, that is the sparsity level. How many anomalous locations are there? We have it 1, 5, and 10. And this was the anomalous distribution we chose. And the prevalent distribution we chose for this model was just the standard Gaussian. And so what you see here, so the color is the sort of a proportion of successes, so successfully fully recovering the anomalous support to failures. So we didn't recover a piece or all of the anomalous support. And so this is telling you that there's a sort of certain point at which we have enough measurements, or we have gone out for enough time to accurately recover the signal. This sort of tan area is perfect recovering the support of the signal. And so so it could be that your application, you're just very restricted in time. You need to figure out the anomalous locations ASAP, and you're willing to do the extra work of taking more measurements and storing them in order to achieve that. And so the good news is this technique will work for that. And you can also see that because we're a little bit thinner on this M side, we gain a little bit more ground by taking more measurements than just simply going out in time. So that's pretty exciting too with this technique. Okay, now that was for that JSM, that was for that first sparsity model. And this was that second sparsity model, or the joint sparse model, where you had the common component and then the sparse innovations, and to sum to make the full signal. So this is going to be our random variable version of that. So I'm just looking at the time, and I'll go ahead and this one, I'll just summarize this one quickly. I won't go through as slowly as for the last one. Okay, so it's a similar setup. And the idea is that what we're going to do is reduce to that previous case, that JSM2 case. And you can probably kind of intuit how we're going to do that. We're first going to estimate that common component, and then we're going to subtract that off. And once we subtracted it off, it looks an awful lot like the JSM2 case. And so then we're able to just apply the previous algorithm to that to finish recovering the support. What we're going to do is, this is the way we're going to estimate the common component. We call this the transpose estimation of the common component. And we're going to compute this, and then we're going to subtract that off, and this new estimate, these new measurements, we're going to then solve by the previous algorithm. So what does that look like? So here's our original setup. This is that JSM3 model, a 3R model that we talked about. And then we're going to take the transpose. So here I've just transposed A, and here's our measurements Y. So this is all the information we have. And we're going to go through and compute, this product. So we're going to go, row dot column, blah, blah, blah. And that's going to estimate the common components. And then we're going to take our, so here's our original measurements. We're going to subtract off this product, and that's going to give us this new set of measurements that we can then use to apply the previous algorithm. So that's kind of what's going on there. And then we have a very similar looking theorem, a slightly different set of assumptions we just have assumptions on our standard deviations, because remember now we don't have any zero mean things. We just have two different mean things. And we can show that this transpose estimation of a common component algorithm, and then using the previous algorithm to recover the JSM2R part, is going to be successful asymptotically. And it's a similar technique. Now we just want to notice that this is sort of in here is a sample mean of a different random variable, this random variable. A cool thing about Gaussians, about the standard Gaussian, is that the expected value of A transpose A is, sort of a scaled identity, right? So that's pretty cool. And then we can invoke the law of large numbers again, because we're dealing with Gaussians. And we can say that this common component in expected value is going to be X. And then we can subtract it off. And then we can apply it's the same idea as before. So that's how we're able to sort of prove that. And so here's some experiments for this one. So now, because we have to do this extra work of recovering the common component and subtracting it off, if these look a little thicker, it takes us more measurements and more time to get to perfect recovery accuracy. But we can do it, and it looks a little bit of a similar shape, right? It's sort of thinner on the M side than it is on the T side. And these were the parameters of the distributions we chose for these experiments. Okay, so we discussed the multiple measurement vector paradigm for support and signal recovery. We discussed work conducting hypothesis tests on mixed observations from a collection of distributions. We cast this problem as an MMV support recovery problem. We introduced two MMV anomaly detection models that were associated with these algorithms, provided some theoretical guarantees for support recovery, and then provided experimental results and sort of explored parameter trade-offs. And here are the references that I had put up earlier in the talk, if there's interest. Okay, so with that, I'll go ahead and stop and see if we have any questions.